sometimes I think you can like watch it on double or triple speed. Okay, so you go back over the lecture in like 20 minutes. Boom. I might talk a little fast, but
do you keep old lectures too?
they're all there from the past 2 years. So what we're going to do today is there from. Okay, it'll be different, but if you want to see, yeah, they're all there. I started actually. I used to just only put the date, but I started putting topics because students were going back, and if I put topics, it's easier to help find it. Okay, let's figure out what functional groups are there. That's vanillin, but let's pick up with the green sheet. Questions about the syllabus? Okay, today in lab we need to meet actually downstairs first. Okay, this room may be used, even if it's not. I like the room over here on the other side of the atrium, first floor. I think it's 1049 or something, but over that way on the first floor. 2:30. Okay, we'll talk there and then we'll go up for check-in. Different from yesterday. There's instructions and requirements for check-in in the lab manual. Okay, please read them. Please follow them, including safety and dress, lab goggles, eyewear. Okay, I think we're ready to pick up on the green sheet. We left off where? 2 constitutional isomers. We did, yeah? Need to know definition, how to recognize constitutional isomers. Let's look at structures with double bonds, CH2O. Let's see if we can put together a structure there. How many valence electrons are we dealing with? Carbon has 4, each H1 is 6, oxygen has 12 valence electrons. So our low structure needs to show all 12. Okay, we want to bond our heavy atoms. Okay, these are simple formulas. Okay, what if we had C12O3, okay, a couple of nitrogens, etc. I'll show you a little trick to that. You don't have to do quite so much systematically. Once we do functional groups, then you can use those as your quick building blocks. Right now it's very systematic, but it's only going to work for kind of simple ones. It becomes too cumbersome with larger structures. This is very important to understand the system. Okay, bond those, right? Then put your H's up there. Where do I recommend putting them? On the carbon, yeah? Okay, how many valence electrons? That's 6. We got 6 more to put up there. There's no more atoms, right? That's all the atoms. We don't have another H to put on the carbon. Okay, to saturate it with H's. We don't have that. The electrons. But when we just put electrons up there, we want to put them up there as lone pairs. We want to put them on the more electronegative atom. Because actually we want to make sure we fill this octet even more so than the other one. Which one's more electronegative? Oxygen, periodic trend, right? Oxygen more electronegative. Let's fill the valence of oxygen first using our extra electrons, lone pairs. There's one lone pair, there's another. What's that, 10? And another lone pair, 12 valence electrons up there. Does oxygen now have an octet?
Yes.
Yes. 2, 4, 6. These 2, which are being shared, but it gets to count. 8 around the oxygen. Okay? Does carbon have an octet? 2, 4, 6. Set. It does not have an octet. So we want to strive for a better structure. Usually all octets is what you want. That's really the golden rule. The first rule you want to look at. We need something better. This is not it. Before we go on, is this typical bonding for oxygen?
No.
No, that's 2 bonds, 2 lone pairs. It's not typical. So what does it say if it's not typical? It's probably going to have a charge. What is the charge of this oxygen? How do you determine charge? Okay, there's formulas out there. Charge is how many electrons does it own versus how many is it supposed to have according to the periodic table. Oxygen's supposed to have 6. This is where we came up with the 12, right? Well, how many is it owning here?
7.
Oxygen owns its lone pairs, and it owns 1 of each bond. Now, there's a difference between an octet count and then how many it kind of owns. When we do the octet count, we're counting them all and we say it's sharing. But in terms of owning, it's almost like, well, how many did oxygen bring to the dance and contributed to this? It's got these, but one of these came from oxygen, one of these came from carbon. So in terms of how many it owns, it's only one of these. 2, 4, 6, one of those makes 7. So oxygen owns 7 in this structure. How many is it supposed to own?
6.
It's only supposed to own 6. So it's got 1 more than it's supposed to. And if you have 1 more electron than you're supposed to, what's your charge?
-1.
-1. Okay? Negative. Usually don't write the 1, just negative, and you want to circle your charges. This is a formal charge. Now, what's the charge of carbon here? I mean, it isn't owned in this structure that we put on the board. 3. It only owns 3, 1 of each bond. That means it's supposed to own 4. It's missing an electron. If you're missing an electron, what's going to be your charge? Positive. Okay? Now, that is a complete Lewis structure. Now, it doesn't mean it's the best, the correct one. Really, I like the term best. It's the best because carbon doesn't have an octet. This is a structure. Lewis structure must have charges, formal charges, if they're present. Okay? So I just went through how to determine charge. You can find a formula or something. It's the same thing. I typically do not give you formulas. I give you explanation. Formulas in your textbook. Okay? I don't like to rely on formulas. I like you to understand. Okay? All right, can we do better here? Well, we can reorganize the electrons. We don't have any more atoms to put up here. Can we place the electrons in a different way? Yes. Carbon needs electrons, yeah? Oxygen sort of has too many. Let's see, do we want to maybe redraw this and say, instead of putting 3 there, let's put the third one over here. That's 12 valence electrons. Now if we do charge, what's the charge of the carbon here?
Minus. Or no.
It's actually minus. What's the charge of the oxygen? Yeah. What about that structure? Do you like that better? Why do you not like that? True. Which one would you rather not have an octet?
Carbon.
What did we say earlier? Oxygen is more electronegative. It's going to be more demanding of having its octet. Okay? Right? Okay. So this is worse. But it is a Lewis structure. It is a complete Lewis structure. It's just, if we assess it, it's not as good as this one. Can we get something better than this?
Yes.
Okay. This is reasonable, and you might see this down the road, this type of polarized structure. That's not good. We'll say this down the road. You never want to leave an electronegative atom without an octet. Okay? Carbon we will see without octets often. We'll see, this is called a carbocation. Okay? Very common. Don't want to have oxygen without an octet. We will see positive oxygen. I didn't say it could be positive, but I say you don't want to have an oxygen with no octet typically. Or nitrogen or fluorine. Okay. How can we do better? What we can do here is we can say, hey, oxygen, we want you to share your electrons with carbon. And I'm going to do mechanism. These electrons, they need to sort of move in here. I'm going to sort of do this. And we're going to show a resonance arrow. And then we're going to show the result of this. And what this means is these two electrons sitting as a lone pair, I want them to fall in as the second bond. Okay? Lone pair. Fall in and now make the second bond. So what does that arrow mean? We now have double bond between there. How many lone pairs left on oxygen?
2.
2. Still have 12 valence electrons. All I did is reorganize the electrons. I made another bond. Now I'm doing this on the board. The molecules obviously, we have to talk about them. Ultimately, this is called resonance, which is just alternative placement of electrons. Now we've got a new Lewis structure. It's the third one. Do you like this one better? Why do you like this one better?
Octets.
Does carbon have an octet now? 2, 4, 6, 8. This is a double bond. Simple right now. Okay? Octet. Does oxygen have an octet? 2, 4, 6, 8. Okay? Everything has octets. What's the charge of the carbon?
0.
It owns 1 electron at each bond. It owns 4. It's neutral. Oxygen's neutral. Everything's neutral here. This is a better structure for 2 reasons. Everything has octets, and all atoms are neutral. Okay? So this is your best structure. This is a reasonable, polarized resonance structure. That's a bad resonance structure. Okay? The reason we talked about. So, this illustrates a mechanism arrow. These electrons move in. This right here is the process we use to show movement of electrons and to help us organize what we're doing. We need to understand the arrow movement. You see how this means we're making this pi bond? That's not chemistry there. That's us doing it on the board, working. It helps us work. But because it's so powerful in helping us work, you're required to learn how to do it. Because it's the language of working and doing organic chemistry. Got to understand that. Okay, what else can we say about this structure? Okay, so this is a double bond. Carbon with double bond. It does have 1 DUS. Okay, you can go ahead and state that there. It's a degree of unsaturation. Because it doesn't have the maximum number of hydrogens that you could put here. Actually, the one up above had CH4O, okay? Remember before? Both of these formos have 1 carbon, 1 oxygen. But that has 4 H's, this only has 2. Turns out 4 H's is the maximum you can have. We'll talk more about it. 2 is not the maximum. So it has less than the maximum. We say it's less than saturated. That C and O is saturated with H's. This is not. It's not saturated with H's. We call that unsaturated. And if you're missing 2 H's, it's 1 degree of unsaturation. I'm just giving you some advanced on what we'll look at DUS in a minute. But since we got this up here, we can set the stage for that. Okay, structures with triple bonds. Let's look at that. HCN, how many valence electrons?
Ten.
Somebody say 10? Yep. Is that right? Anybody? 4, 5. Nitrogen, group 5. Okay, yeah, 10 valence electrons. I'm going to what? Bond the C and the N together? I mean, that's all we got. I mean, where do you want to put the H's at?
C.
I recommended putting them here. Okay. By the way, we're not doing any hybridization or bond angles yet. So if I draw bond angles that aren't right, we're not really looking at that. That's it, right? That's all we got. Now, could you have a structure where the H is bonded to the N? Possibly. I'm showing you a very systematic way to get you an answer. Okay. Okay, that's two for, we got how many? 6? That's 3 lone pairs. Where do you want to put them? 1, 2, 3. All your electrons are there. Do you like that structure? Well, carbon does not have an octet. Not standard bonding. What's the charge of the carbon here?
Plus 2.
2 plus, right? It's only 2 electrons, 1 of each bond. How many is nitrogen owning here? 2, 4, 6, 1 of these, 7. It's only supposed to have 5, so what's this charge?
2 minus.
2 minus. By the way, what's the net charge of this guy?
Neutral.
It's net neutral. But we know that from here. How do we know it's net neutral?
No charge on it.
Because there's no charge shown. I mean, if it was charged, I should show you a charge. I can't hide it from you. Okay? This is a neutral molecule. Okay? Yeah, it's neutral. It's net neutral. Maybe we could show a structure that everything is actually neutral. Do you like this? No. Carbon doesn't have an octet. It's okay, but one thing, you usually don't want to have 2 plus and 2 minus in organic chemistry. 1 plus and 1 minus is usually the max. Now in Gen Chem and with inorganics and metals, 2 plus, 3 plus, that's fine. All right, what can we do to get to a better structure systematically? Do you want to ask nitrogen to start sharing? And maybe these electrons move in here? What does that mean to you?
Double bond.
WDM, what does arrow mean?
Mechanism.
Electrons moving in to make another bond? Okay, well let's show that. This is a resonance arrow. By the way, I don't cover resonance until test 3. Okay? But by the time we cover it, we will have used it a lot. Most textbooks and most courses cover resonance first week. I think it's way too early. But we're introducing resonance. But there's I don't think you can fully appreciate resonance until you become more savvy and experienced in trying to do test 3. Okay, what does this arrow mean to you? Just moving the electrons in. And now what do we have between the C and the N?
Double bond.
Double bond, 2 lone pairs left. That's all we did. Because everything we have here has to be shown by the arrow, or multiple arrows. That arrow gives us this. Okay, do you like this structure? Charge of the nitrogen.
Plus. Or minus.
2, 4, 5, and 6.
No, it's minus. It only needs a bond.
Minus. Charge of the carbon. That means it's owning. It owns 1 of each bond. That means it's supposed to own. Missing electron, so it's positive. Here you go. Making another bond got us to plus and minus instead of 2 plus 2 minus. Do you like this structure? Carbon still does not have an octet. Nitrogen has an octet in both structures. But we're trying to make sure carbon also has an octet. What can we do?
Triple bond.
Let's share again, nitrogen. Come on, nitrogen. We need to do some sharing here. Now what do we have? What does that arrow mean to you? Now what do we have between the C and the N?
Triple bond.
Triple bond, how many lone pairs?
1.
1 lone pair. Nitrogen has an octet. 2, 4, 6, 8. In terms of how many it owns, 2, 3, 4, 5, how many is it supposed to own?
5.
Neutral. Does carbon have an octet?
Yes.
2, 4, 6, 8. Charge. Neutral. Everything's neutral. Everything has an octet. This is your good structure. Could there be a constitutional isomer? Like I said, possibly if you put the H over here. I think that structure would have to have charge, though. Maybe somebody will look at it. This is typically when you see ACN. So we have triple bond, right? Is that 10 valence electrons? 2, 4, 6, 8. Yeah. Okay. So there we go. This is actually 2 DUS. because that's not the maximum number of H's for C and N, for a one carbon, one nitrogen. What would be the maximum number? Well, what if we just put C and N together and then just started putting as many H's around as we could? How many would we put on the carbon? 3. How many would we put on the nitrogen? 2, because it would have a lone pair. If you put 3 on the nitrogen, it would have to be charged, because it would be typical. That's saturated, and that's how many? It's 5 H's. This is unsaturated. Every 2 you're missing is 1 DUS. It's missing 4. Here, that's 5, it's 1. You divide 4 by 2 and you get 2. Okay, TDUS. Actually, let's now look at DUS. That's in the other handout. By the way, anybody look up the half-life of C14, C11?
5,000 years.
What?
Or 5,400 years.
Carbon 14, is it 5,400 years?
I think so.
Yeah, it's something up there. Yeah. It's a long half-life. That's why, you know, the dinosaurs from 80 years ago, we can, that carbon 14 is still around and we can still measure it. What about carbon 11? 20 minutes. Huge difference. 20 minutes and 5,400 years. Whenever they do carbon 11 PET imaging, it has to be done quickly. Usually you have to make the carbon 11 on site. That's why they make carbon F18 over here on Central Avenue, so they can get it to the hospital real quick. They make it in Colombia, but they're having problems with the shipment. It's too slow. Okay, DUS. DUS, I introduced a little bit. It can be determined from structure and from formula. Okay, I'll just sort of take it through here, and at some point I'll step back and say, okay, let's summarize things. Yep. One double bond is going to be 1 DUS. Basically, each pi bond is a DUS. We haven't described pi bonds yet. One triple bond is going to be 2 DUS. One ring is going to be 1 DUS. 1 degree of unsaturation. Okay? We just did HCN. And so this may be a repeat. Actually, it is. HCN has 2 pi bonds. That's because your first bond is going to be a sigma bond. We'll start doing this when we're looking at hybridization. Then when you make the double bond, you're adding a pi bond to the sigma. So double bond is 1 sigma, 1 pi. Triple bond is where you end up adding 2 pi bonds to the sigma. So the triple bond is 1 sigma and 2 pi. Each pi bond is a DUS. I see 2 pi bonds, and so I have 2 DUS. Each DUS means it's missing 2 H's. 2 DUS's means it's missing 4 H's compared to max. Max would be like this structure, where we said it's saturated with H's, the maximum it can have. This is not. Instead, we have pi bonds, which are DUS in terms of our bookkeeping. Look over here. If you just have 2 carbons, what's the maximum number of H's? What if you just put all H's around it, you end up with 6? But you could have a structure where there's only 4. But you'd have to have a double bond. And this is no longer saturated. It's missing 2 H's, that's 1 DUS. We also see that it has 1 pi bond. And that tells us it's 1 DUS. You can tell DUS from structure, which would be looking at the pi bond, or you can tell it from formula, which would be looking at the number of H's present, as shown below. Once we get through here, we'll do some examples. A ring. Like I said, a ring is DUS. If you have 3 carbons, you can show something like this, totally saturated. No pi bonds. By the way, don't look at structure. You've got 3 carbons, what's the maximum number of H's? How can you quickly tell?
8.
value right below. I
Two
hope you would all
sequence.
have, because this was coming up today, and maximum number of H's is what?
8.
2n plus 2, where n is number of carbons. Okay, 3 carbons. 2n plus 2, where n is 3. I haven't had math in a long time. What is it?
6
Comes
plus 2.
through 6 plus 2 is 8. Okay. How many H's are there? 8. 3 carbons saturated and have 8 hydrogens. That's the 2n plus 2. Okay. Now, if you want to make a ring and join the carbons together, okay, and make a circle with a ring, which plenty of rings in organic chemistry, we can do this. But if you look at it and you put maximum H's on it, each carbon can only get 2. And that's only 6 H's. And 6 is not 8, so you're missing 2. And every 2 you're missing is what?
1 DUS.
1 DUS. A ring is going to be a DUS, because you have to essentially, if we want to bond these 2 carbons together, you got to get rid of 2 H's. Get rid of 2 H's, then the carbons can bond together. Ibuprofen, how many DUS do you see? Now, there's a whole bunch, and sometimes my pi bonds are kind of not precise, but there's none out here.
2.
That is just boom, boom. That's 1, 2, that's 4 carbons out there. How many DUS do you see?
2.
I see, you see, this is a pi bond. It's just not drawn precisely. I see 3 pi bonds, 4 pi bonds. Okay, we haven't done hybridization yet. 4 pi bonds in a ring, 5 DUS. Okay? It's 5 DUS. This will help you with down the road, okay? We're introducing it. We'll start using it. Question? Do what? It's, you can have both just as equal. I mean, it's all types of carbon compounds. You might be talking about stability or bond strengths because a pi bond is weaker. If you please speak loud, guys. People need to be able to hear you in the back. I can't hear you. Too many Bon Jovi concerts. AC/DC. And we want to make sure to pick it up on camera, okay? Make sure you yell into the back row. Formula. Okay, hydrocarbons, which just means it's hydrogen and carbon, CH only. 2n plus 2. Okay, you can go through this. I've already pretty much done that. When heteroatoms are present, like oxygen, nitrogen, different from carbon. When they are present, how does this fit in? Same as above, except a halogen is going to count as an H. Because if you look at the formula, here's Prozac. You can't just do 2n plus 2 and say, well, there's 18 H's, and okay. Because there's more to it than that. You've got the, how do you account for this other? And really, you want to turn this, what is this, how does this affect the H's? It affects the H's this way. A halogen counts as an H. So I got 3 F's. So that means it's adding to the number of H's. What does oxygen do? You just ignore it. Oxygen plays no role here. Nitrogen, you actually have to subtract an H. It has to do with the number of bonds those make. Okay? So using that, I can turn this formula into C17H20 if I know what these counts as. Because that adds 3, so that makes it 21. But nitrogen subtracts 1, so I go back to 20. And oxygen, you don't just ignore. Now I'm going to sort of this formula. C17, how many are maximum?
36.
36, yeah? 20 plus 2? I don't see 36. How many am I missing?
16.
16. Divide that by 2. 8 DUS. Right? If we look at the structure, see, we did that by formula. Caution, you got to be careful here what they count as, because I see a lot of students starting with like the 20. Or if you go backwards, you got to, sometimes nitrogen adds, it's because you're going the wrong way. I don't have a good example, but be careful here. Don't just, that may come up in something. Let's look at Prozac. Isn't it here?
Yeah.
There it is. Okay, this is page 2 in the workbook. Lots of questions here, stuff you need to begin working on. Formula, DUS, functional groups. Do you see 8? There's Prozac. Do you see the 8 DUS? How many pi bonds? It's actually 6. We haven't did DUS hybridization yet. 6 pi bonds and how many rings? 2 rings. Okay. Here's your 8 DUS. So we did it by formula, and we can look at structure and get the same answer and make sure they're the same. Okay, formal charge, we did that, right? Carbon with 5 bonds, not on this planet. Okay? If you ever find one, you don't get a Nobel Prize. Carbon only has 4 valence orbitals. It can't make 5 bonds. Silicon can. Well, silicon has d orbitals. Okay? I will find lots of, maybe not lots, I will find carbon with 5 bonds this semester. Right, grading. All right, watch out for it. Okay. Expanding the octet, there's a handout in here about that. I'm not going to go over it. It's sort of miscellaneous. Also, boron. Boron's hard to get an octet with boron. So you can think about it, especially when we do hybridization. Resonance. I introduced resonance here some. Resonance is, I give you a little definition here, when more than one acceptable Lewis structure can be shown. But when you do resonance, you typically want to assess which structure is best. Okay. And we talked about, you'd rather have no charge, and you want everything to have octets. That's best, right? Let's look at the functional group page. Okay, your functional groups are your common arrangements of atoms with typical bonding. They're sort of like building blocks. Instead of putting every little structure together one atom at a time, you can just say, hey, let's just throw up an ester. Okay? Let's go through these. At the top, it's sort of very generic. These are so generic, sometimes they're not even called functional groups. But they're major structural types. Okay, your alkanes. These are just, first off, this table is hydrocarbons. That is just compounds with hydrogen and carbon, no heteroatoms. An alkane, this is carbon and hydrogen. Alkane is going to be all saturated. Okay, you're not going to find any pi bonds. That's just ethane, octane, propane in your gas grill. It's just saturated CH compound, all single bonds. If you start putting a double bond between the carbons, Carbon-carbon double bond, that's an alkene functional group. The compound as a whole can be called an alkene, but usually when we say alkene, we'll focus in and look at that carbon-carbon double bond. Okay? Ane versus ene. Now you got alkyne. This is going to be carbon-carbon triple bond. Now we will look at alkanes for test 1. The chemistry is not that extensive because you can't do much with them. Once you get a pi bond in the compound, it allows so much more reactivity. One important thing with alkanes is you can burn them and heat your homes and your gas grills. These are covered, I cover these are in test 2, pi bond chemistry. Okay. Test 3, I'll maybe mention it a little lower. Aromatic compounds. Now they're only showing one here, they call it a phenyl group. This is a benzene ring. This is the 6-membered ring with 3 pi bonds. Prozac has 2 benzene rings. Okay. The benzene ring is your granddaddy of all aromatic rings, the most common. And organic 2, we have a test that's just dedicated to aromatic chemistry. When we talk about aromaticity, benzene will be the main compound we look at. Again, benzene was discovered in the lamps that used to heat the streets 200 years ago. Michael Faraday actually distilled it and isolated it. I don't think they knew the structure back then what it was, but they knew it was a pure compound. They also knew that it was a hydrocarbon and that it had an empirical formula of CH. Okay. Now it turns out that it's C6H6, but when you determine empirical formula, CH has the same ratio as this. Okay. Structure wasn't sort of elucidated until about 50 years after the compound was actually discovered. Okay. That's your benzene ring. All right, compounds containing heteroatoms. Halides, very common, fluorine, chlorine, bromine, iodine. Okay. R group, an R group is just a plain carbon group. It can be 1 carbon or it could be 17. There's no R on the periodic table. There's an RU and RH with no R. So R was chosen as sort of a generic descriptor for carbon groups. This is a carbon group bonded to a halogen. X is typical for halogen. Okay? So RH. A specific would be like methyl bromide or bromomethane. Of course, halogen just makes 1 bond, 3 lone pairs, right? Halogen's always on the periphery. Got to get used to structures. Obviously, these H's are not bonded to that bromine. The H's are on the periphery of the carbon, right? You do the structure out. You would not put the H's are actually right here, right? Here's your good structure. But when things are written, you got to be careful about this and recognize it. Sometimes people may be a little bit more precise and write it like this and put the H's sort of on the other side. But not always. Probably more likely to see it like that. Okay. Alkyl. That's like an alkane halide, but the ill means it's sort of a fragment. Okay. Arohalide is where you have an aromatic ring bonded to the halide. For example, a benzene ring that's bonded to the chlorine. That would be an aryl halide. Now, this is where the chlorine replaced an H. Remember in the DUS how chlorine... Okay. What's the formula of this? C...
6H5.
6H5Cl. Because if it was just benzene, it would be C6H6. The chlorine is there, and it's substituted an H, so it's there. DUS. How many DUS do you see in the structure?
4.
1 ring, 3 bonds. 4. Okay. How many do you see in the formula? What's saturated for C6?
4.
14. How many does it have?
6.
How many?
6.
It has 6. Because first thing you want to do, how does chlorine count?
Hydrogen.
Right. So you manipulate it to make it look like that, and then you can see. Okay? Chlorine just replaced the H. That's why when you're coming backwards, it just counts as an H. Okay. Alcohols. This is where you have a carbon group bonded to an OH. For example, a methyl bonded to an OH. Now, since oxygen makes 2 bonds, you can't just have CH3O unless it's charged. So you have to have something else there. Now, see, oxygen can just be slipped in. You can just get rid of it and have a good structure. Same number of H's. All right, let's get away from DUS and let's go through these here. If you have an oxygen with carbon groups on both sides, that's called an ether. Variety of ethers. Commonly when you hear the compound called ether, that is diethyl ether. It's so common that it's just called ether. It's actually used in the Civil War as to knock people out. Okay, standard bonding, right? Everything. Nitrogen compounds. If it's saturated, it's going to be an amine. Like that. So nitrogen compound, everybody agree that's saturated? The maximum number of H's? I see no pi bonds or rings. A nitrogen bonded to an R group. Okay. Now, nitrogen could bond to 1 R group, it could bond to 2 R groups, or it could bond to 3. All the bonds of nitrogen could be R groups. That's what this is saying here. If it's bonded to 1 R group, it's called a primary amine. 2 is a secondary amine. 3 would be a tertiary amine. Example of a tertiary amine would be something like put the carbon H's on the outside. Maybe like bonded to 3 methyls. Okay? So that'd be a tertiary amine. Note the difference here. Oxygen with 1 R group is an alcohol. You put 2 R groups, it's no longer an alcohol. It's now an ether. But with nitrogen, you start adding R groups, the name doesn't change. Okay. Thiol. Thiol is analogous to alcohol. Sulfur is below oxygen. It's the same exact bonding. And so you see how the similarity is. It's called a thiol. Sometimes called a mercaptan. Sometimes biochemists say that. Thiols are very common in biochemistry. If you have a sulfur with 2 R groups, that's analogous to the ether, right? That's called a sulfide. Sometimes you may hear it called a thioether, because it's analogous to the ether, but it's the sulfur. It's sort of scientific for sulfur is thio. Okay, the functional groups on this side, at the top are the ones that contain a carbonyl group. Carbonyl is C double bond O. Some people may say carbonyl. I say carbonyl. Carbonyl is not an exact functional group, even though this book sort of listed it that way. It's not. Carbonyl is a component of many different precise functional groups. Aldehyde. You have a carbonyl with an H on one side and a carbon group on the other, that's an aldehyde. Of course, the carbonyl's got standard bonding. Oxygen, 2 bonds, 2 lone pairs. Carbon, 4 bonds. All these have standard bonding. Ketone, that's where you have a carbonyl R groups on both sides. That right there is acetone. That's what we wash glassware in the lab with. Fingernail polish remover is often acetone. Many of you have this in your bathroom or the emails. Fingernail polish remover. Carboxylic acid, R group on one side, OH on the other. And the OH is acidic, that's why it's called carboxylic acid. Carboxylic acid is the only acid that you're going to see on this page. It's called an acid. Of course, many things can act as acids. Water can act as an acid. But do we call water an acid? No. Ester. Ester is like the acid, except instead of OH on one side, it's OR. An ester. Amide. Amide is where you have the carbonyl carbon group on one side, nitrogen on the other. Now with the nitrogen functional groups, if you start adding more R groups, the name doesn't change, just like amines. If you start adding more R groups, it can become secondary or tertiary. This is the number of carbons attached to the nitrogen. What type of amide is this? Primary, secondary, tertiary? Primary. Nitrogen's attached to one carbon. Okay? Note, some students want to say when you look at this, that's an amine and that's a ketone. No. Altogether, it's an amide. Okay? Acid chloride. This is where you have R group on one side, chlorine on the other. Usually with this type of thing, you don't see like acid fluoride or bromide. Just chloride. These tend to be very reactive. Chemistry, this is covered in organic 2. Acid chloride. That's really where the OH has been replaced with the chlorine, so it sort of comes from the acid. It's actually no longer an acid. It's just derived from it. There's 2 additional ones I want you to know. Nitrile. This is the C triple bond N. Of course, the N's going to have a lone pair, standard bonding, R group. Sulfonamide. This is another type of amide, but it's not the simple standard amide, which, by the way, is called a carboxylide because it has the carbonyl group. This is always called long sulfonamide. This is where, and this is no longer a carbonyl, this is where you have an SO2 nitrogen instead of the CO nitrogen. So it has the sulfone group. It's sort of like a sulfonamide, but it's pronounced sulfonamide. Sulfonamides are common in a lot of drugs, like antibacterials, antidiabetic drugs. There's some below. We're about out of time. Let me set the stage for next time. Please look at this. Some of these are sort of identified for you to give you some practice. Okay. There's 2 others down here to know. If the amine is attached to an aromatic ring, it has a special name. It's called aniline. And if the hydroxyl group is attached to an aromatic ring, it's got a special name. It's phenol. Please start looking at the functional groups, like page 2 in the workbook. Please look ahead. We'll hit hybridization hard on Monday. As we dismiss, if I can find it, remember we're meeting downstairs. I'm going to show vanillin. There it is. Can we recognize any functional groups in vanillin now? See this aldehyde up here? Yeah. What is this?
Phenol. Phenol.
It's an alcohol bond to an aromatic ring. It's pronounced phenol.
Phenol. Ether.
Ether. Very good. Doesn't matter if it's bonded to an aromatic ring or not. It's an oxygen with carbon groups on both sides. It's an ether. Okay, guys, have a good weekend. Be safe. See some of you this afternoon downstairs at 2:30. No, we're going to go over here. It's a smaller room.
Who wants to be a good student? That's because you talk to yourself a lot.
Seal was this.
Yeah, all about it. You're good.
Are you not moving, sure?
My stomach hurts so much.
Okay. I was wondering. Are you not moving? I'll stay here with you.
Hey, Doug. You know how we were talking about when it's in the middle?
You see where I
Saturation, when it's in the middle, it's nitrogen. Is that only the nitrogen in the middle, or is it also nitrogen?
No, it's if it's formula in general. Anyone in the formula.
y'all are crazy for going to free
Yeah, it doesn't have to be like
I was so tired, like, me and Will like midnight doing video, and I get a Snapchat from it. It was already really saying, on the way to Freakology with a taco, no big deal. I'm like, I'm sitting in bed, like, I'm dead tired.
You're safe for another round? You're safe for another round?
Physics is in the same class and it's
I like your schedule better. Mine is that I have orgo, then I have hour break, then gen X, then hour break. So I'm here from 8 to 1.
I like getting like all my stuff.
Exactly.
I think Jackson did already. I think he's already started off the year. But he's usually what? I don't think I'm sick. I think it was I had bad mornings. No, shit, I still have this. Yeah, you screwed us over. Who do I eat, man?